In our previous discussion on forces, we introduced Newton's laws of motion. The second law of motion, acceleration equals net force divided by mass, is kind of the equation that we use to calculate any consequences from applied forces. In order to be able to usefully generate the equations that we use for Newton's second law, it's good to have a picture of what's going on. A picture of the forces acting on an object is called a free body diagram, or you might see it called a force diagram. And I want to establish a few ground rules. These are the rules that I'm going to follow, and I strongly encourage you to follow most, if not all, of the rules when it comes to creating these diagrams. And once you have the diagrams, you do the work necessary to make them complete. Using Newton's second law becomes relatively sane. So let's look at these steps one by one. When you read a problem, it's going to tell you that something is happening to an object. Now, it is quite possible that this object is in contact with a surface. Maybe it isn't, maybe it is. If it is in contact with a surface, you should start by drawing a line to represent that surface. Maybe it is on a flat horizontal surface, you draw a flat horizontal line. Maybe something is being pushed up against a vertical wall. Well, you draw a vertical line to represent the wall. Perhaps it's on a ramp. Draw a ramp at the angle, hopefully the angle is given in the problem. Draw at some angle, a straight line. Then draw the object on which the force is acting. And you don't need to be detailed. As it says, don't be Picasso unless you're Picasso. And I didn't notice that last name among anybody in this class. So if it's a box or something, draw it as a rectangle. You might find, especially later on in this semester, that you might need to represent it as a circle. Okay, that's okay. Just keep it simple. Once you have the surface and the object, the next thing I would do is off to one side or the other, sketch in a small pair of Cartesian coordinate axes, an x-axis and perpendicular to it a y-axis. Now, the tricky part is figuring out the orientation of that axis. The x-axis doesn't have to be strictly horizontal and the y-axis vertical. In fact, there will be many situations in which we find that the best orientation of the x-axis is non-horizontal. For instance, if you have a block sliding down a ramp, you would probably want the x-axis to be parallel to the surface of the ramp, which would make the y-axis perpendicular to it. There is no restriction on the orientation of the x-axis. It does not have to be horizontal. If you know the direction of the acceleration, I think it's in your best interest to have the direction of the x-axis be in the direction of the acceleration, or at least the direction of the negative x-axis, but preferably the x-axis in the direction of the acceleration if you know it. If you don't know the acceleration, it's completely up in the air, then it requires a little bit more concentration on the forces. Look at the forces, examine their directions. You're going to see that several forces are parallel or perpendicular to each other. What you want to do is you want to orient your Cartesian coordinate system to maximize the number of forces that are parallel to at least one of your axes. So if you have some perpendicular forces, you can orient it so that the x-axis is parallel to one of them and the y-axis is parallel to the other. Doing that will save you stress in the long run when you start doing a mathematical analysis. So if you pay a price up front, a small price up front, It's going to pay off big dividends later. What's next? You draw the forces. Some of the forces will be implicit, and we'll discuss that over the duration of this lecture. But some of them will be explicitly mentioned in the problem. There might be a push or a pull on an object. There might be a rope attached to the object, something. There will be something in the text of the problem that discusses one or more specific forces, and then you might have to draw other forces that are implied, like the gravitational force. But as I said, we'll get into that over the course of this lecture. When you draw those arrows, they should point in the direction of the force. They should be somehow connected to the object. I don't care if you attach the head of the arrow to the object. I don't care if you attach the tail to the object, but it should be attached to the object. It should point in a good representation of the direction of the actual force. And if possible, if you have some idea as to how strong the force is, if it's a strong force, you draw it with a long arrow, and if it's a weaker force, you draw it with a shorter arrow. If you don't know anything about the strengths of the forces, you're kind of out of luck on this. But if you have some idea, it helps in the long run if you draw your arrow lengths accordingly. When you know what is causing a force on your three-body diagram, label it. If it's the gravitational force causing it, call it F subscript gravity or F subscript capital G. If it's frictional force, you can write F subscript friction or F subscript capital F. If it's a push or a pull, F subscript push or F subscript pull. But I recommend using capital F time and time again. You might not see that in the textbook. The textbook might say, well, a normal force will designate with a capital N. A tension will designate with a capital T. I don't like that because it's, in my mind, easy to lose sight of the fact that all of these are forces. A force is a force, of course, of course. It does not matter what's causing the force. It is a force. And representing each of them as a capital F, I think, helps drive home that point. There's nothing special about a normal force compared to a gravitational force, compared to a tension, compared to a push. They're all vectors, they're all measured in newtons, and they all point in a direction. You've drawn the arrows. You've even tried to draw the arrows in the correct direction, and you've tried to give them reasonable lengths. But I think it's good to be very specific, very numerical. Not only do you write down the designation of the force, but next to it, you write down the numerical angle that the force makes with respect to the positive x-axis. This is key to making your later calculations much simpler. Make all of your angles measured with respect to the positive x-axis. Label those angles next to each force on your free body diagram. And even where you think that it's obvious, you'll find forces that are parallel to the x-axis. They're at 0 degrees. You'll find forces that are parallel to the y-axis. Those would be at 90 degrees. If it's in the negative x direction, those are at 180 degrees. And if it's in the directly vertical down along the negative y-axis, if that's the direction of your negative y-axis, that would be at 270 degrees. Write out those numbers. It will pay you dividends in the long run. If you happen to know the acceleration, or at least the direction of the acceleration, just sketch that lightly in. I typically use a double arrow rather than a single arrow. A single arrow for the forces acting on an object, a double arrow to represent the direction of the acceleration. If you don't know the acceleration, this is no big whoop, but it might help confirm your choice of direction for the x-axis. Let's take a look at drawing a free body diagram in the following example. We have a 27.2 kilogram crate on a horizontal floor. we have a 51.1 Newton force pushing to the left and an 18.5 frictional force opposing it. So we have a floor and we have a crate. Now, there are some forces here that are very obvious. There's the 51.1 Newton push to the left. There's a frictional force of 18.5 Newtons. Now, it says it opposes the force to the left. That must mean that the frictional force is to the right. So, we have our x-axis, we have our y-axis. There's no reason to be anything but traditional here. And we have our force to the left of 51.1 Newtons, and we have our force to the right of 18.5 Newtons. I've also tried to draw these forces acting on the object at roughly the location where it really is. So, if you're pushing a box, you might not be pushing it at the very center. Maybe you're pushing it a little ways from the top. I don't know. But the frictional force is going to be acting very close to the surface. So I've drawn that arrow very low on the box. It's basically at the level of the floor where the frictional force is most directly acting. It's not super important now, but it's a good habit to get into so that when we discuss ideas of torque in a later chapter, you'll kind of be prepared for it. So try to draw the forces at about the location where the forces are acting. Don't stress over it, but put some thought into it. Now, there are two other forces that are present here. We assume that this crate is on Earth. There's nothing in the problem to indicate otherwise. I don't know of any other locales in the universe that have a crate on them. So we assume it's near the surface of the Earth. There's a gravitational force acting down on it. The crate is trying to fall through the floor. Of course, the crate is not falling through the floor. It's not falling through the floor because the floor is exerting an upwards pressure on the crate to keep it from falling. So there's an upwards force of the floor on the crate, and there is the downwards force of gravity trying to pull the crate down. Next, we label our forces. We have the pushing force and the frictional force in the horizontal direction. We have the gravitational force, and I have labeled this the so-called normal force. We'll discuss this in a little bit more detail later, but basically a normal force is always perpendicular to the surface with which the object is in contact. The crate is in contact with the floor is horizontal, the normal force is going to be vertical, and it's going to point away from the surface. These are the four forces acting on the block. As I said, I've drawn the pushing force longer than the frictional force. If you look at the normal force and the gravitational force, it looks like that they have roughly the same length. I honestly don't know the values of the gravitational force and the normal force. But I'm taking advantage of a fact here. This block is not moving in the vertical direction. If it's not moving in the vertical direction, the y component of the acceleration must be 0. If the y component of the acceleration is 0, the y component of the net force must be 0, which means that any upwards force must be balanced out by a downwards force. So I've drawn those forces to be the same length because I have no reason to think that this block is moving in the vertical direction. So those forces must cancel out. And there are no other vertical forces mentioned in the problem, so it's just those two. What about the angles? If it is parallel to the x-axis, it is at 0 degrees. If it is parallel to the negative x-axis, it's at 180 degrees. If it's parallel to the y-axis, it's 90 degrees. If it's parallel to the negative y-axis, it's 270 degrees. I point out, though, that you could write the gravitational force acting at an angle of negative 90 degrees. If you know why, great. If you don't know why, don't worry about it. It's not important. I just include it for the sake of completeness. there is my guesstimate for the direction of the acceleration. I figure that the pushing force is greater than the frictional force, so the pushing force wins, meaning that there's going to be a push that the block is going to move to the left. And so I've drawn the acceleration to the left, and I've even indicated the angle at which I expect the acceleration to be, 180 degrees. Now let's look at an example of an object on a slope. We have a 1,138 kilogram car, and it is rolling down a relatively steep hill. 22 degrees is quite steep for a road. So what's this free body diagram going to look like? We have it at 22 degrees, so there's my road, there's my hill, and there's a car on it. Now, unlike what I said earlier, I did go full Picasso on this. What I've drawn here is a McLaren F1, the most amazing car ever made. I just did it in a Picasso cubist style. Anyhow, what are the forces? Well, we need a Cartesian coordinate system, and this is going to be a case where we want our coordinate system with a tilted x-axis. I'm going to make the x-axis parallel to the ramp. Now, what are the forces acting on it? There's the gravitational force. The gravitational force always acts straight down. There's a normal force. The car is in contact with the road. Because there's this contact with a surface, there's going to be this normal force that points perpendicularly away from the surface. And then you see the third arrow pointing uphill. Unless explicitly stated otherwise, you have to assume the existence of friction. Only if I had said, if the road is icy or extremely slippery, in that circumstance, maybe we can say the frictional force is virtually zero. But unless you see something explicit like that, you have to assume that there's going to be some friction. The frictional force for a moving object opposes the direction of motion. This car is rolling down a hill, so the frictional force must be directed uphill. And then we get to our angles. The coordinate axes are tilted. Please be aware of that. As a consequence, the x-axis is parallel to the ramp, the y-axis is perpendicular to the ramp. Since the normal force is perpendicular to the ramp, meaning it's parallel to the y-axis, it must make an angle of 90 degrees with respect to the positive x-axis. So I've drawn the normal force at 90 degrees. The frictional force points directly uphill. That means that it points in exactly the opposite direction as the positive x-axis, which points downhill. So if it's in exactly the opposite direction of positive x, it must be negative x, and that makes an angle of 180 degrees with respect to positive x. And then we have gravity. And this is the annoying person right here. The gravitational force is not parallel to either axis. And yet, I've written an angle for it, 292 degrees. What I can geometrically show is that for this line acting straight down, acting on an object on this 22-degree ramp, consider the direction of the negative y-axis. The angle between the gravitational force and the negative y-axis, I can geometrically prove, is the angle of the ramp's slope. If the ramp makes an angle of 22 degrees with respect to the horizontal, then the angle between the negative y-axis and the gravitational force is 22 degrees. Same angle. So consider the x-axis is 0 degrees, the y-axis is 90 degrees, the negative x-axis is 180 degrees, the negative y-axis is 270 degrees, but then I have to go an additional 22 degrees to get to straight down. So 270 degrees to get to the negative y-axis, another 22 degrees to get to the gravitational force. 270 plus 22 is 292 degrees. It sounds painful, but we're going to see that this is much less painful than I think other ways of doing it. This is, I think, the least painful way of doing it. It says that the car is rolling downhill, might be accelerating downhill, could be going downhill at a constant speed. The text of the problem doesn't say one way or the other. Could even be going downhill and slowing down if the frictional force is enough. Problem doesn't say. But if there is an acceleration, it's going to be in the direction of motion or maybe opposite, but it's still going to at least be parallel. And so I'm just assuming that the acceleration is in the positive x direction. I can't be so sure of this direction, but it's going to be parallel to the surface one way or the other. It's a guess. Now, when you have to use Newton's second law and there's more than one force acting on the object, we have to find the net force. We have to add up the forces, and in order to do that, we have to break them down into their x and y components first. I can't stress the importance of this enough. In order to get the x component of the net force, we add together the x components of the separate forces. And in order to get the y component of the net force, we have to add together the y components of the net forces. This is why I recommend measuring all of your angles with respect to the positive x-axis. Because if you measure all of your angles with respect to the same positive x-axis, then all of your x components will be generated using cosine, and all of your y components will be generated using sine. You don't have to think about it once you've correctly determined all of your angles with respect to the positive x-axis. If we go to our first free body diagram with the crate on the horizontal floor, and you see the recreation of that slide right here, what would Newton's second law applied to this look like? Now, Newton's second law says acceleration equals net force divided by mass, but I can do a little bit of algebra and say that the second law says net force equals mass times acceleration. So I'm going to try and find the net force. But to find the net force, I need to do the x component and the y component. Now, because I've measured all of my angles with respect to the positive x-axis, have I used that expression enough? I can say that the x component of the net force is 18.5 times the cosine of 0 plus 51.1 times the cosine of 180 plus the normal force times the cosine of 90 plus the gravitational force times the cosine of 270. I can just write that out. And I can plug these numbers in on my calculator. And it turns out that we get that the x component of the net force is negative 32.6 newtons. Magnitude times cosine plus magnitude times cosine plus magnitude times cosine, add them up. Because you have taken all of the angles into account, measuring them with respect to the same reference, you are using plus in between each of these terms. And the value of the angle will take into account whether the force has a leftwards component or a rightwards component. Trust the numbers. In this case, we get negative 32.6, and you might wonder, well, how could I do that when I don't know the normal force or the gravitational force? And the answer is the cosine of 90 is 0, and the cosine of 270 is 0. I don't care what the normal force is, when I multiply it by 0, the x component is 0. Ditto with the gravitational force. Now, we could have looked at the free body diagram. The normal force is perfectly along the y-axis. The gravitational force is perfectly along the negative y-axis, That right there should tell you that the x components are 0. But it's comforting, I think, to see that the numerical calculations back up that observation. It's a good confirmation that you're proceeding in the right direction. What about the y component stuff? And as I said earlier, the crate is not moving in the y direction. It's not bouncing up and down. There's nothing in the problem to indicate that there's any vertical motion whatsoever. It's just sliding across the floor. Aside from a few bumps, which we ignore, it's entirely in the horizontal direction. So the fact that there is no motion in the vertical direction says that the y component of the acceleration is 0, and that in turn tells me that the y component of the net force is 0. Therefore, all we have is a non-zero x component. The y component is 0, so the net force is strictly parallel to x. I can say that the net force is 32.6 newtons at an angle of 180 degrees with respect to the positive x-axis. Hopefully that makes some sense. If it makes some sense, then you should be able to answer this question here. We have another block on a horizontal surface. You see the different forces indicated here, and the question is, which of the following answers is best indicative of the net force acting on the object? Is the net force 35 newtons up? Is it 35 newtons down? Is it 25 newtons to the right? Is it 35 newtons to the left? Or am I trying to trick you and it's really none of these? Think about the problem. If you have questions, ask them at the start of class. Now, I want to discuss some of these commonly occurring forces. So like I said, some of these are implicit. The gravitational force and the normal force can be implied. Ditto for friction and tension. So I wanted to give some mention of these four. The gravitational force, you live with it all your life. You're used to it. And the thing about the gravitational force is that in the absence of air resistance, it induces the same acceleration for any object, no matter what its mass is. So we know that the acceleration due to gravity is going to have a magnitude of g, little g, close to the Earth's surface. That means that the acceleration due to gravity is going to have a magnitude of 9.8 meters per second squared. To put that into context, 9.8 meters per second squared is a pretty good acceleration. The top street legal cars can have, at least for short bursts, they can have accelerations as high as about 9.8 meters per second squared. But it's not anything that they can maintain. You see that 9.8 meters per second squared means that every second your speed increases by 22 miles per hour. So you start at 0. After 1 second, you're at 22 miles per hour. After 2 seconds, you're at about 44. After 3 seconds, you're at about 66 miles per hour. In just 3 seconds, you're traveling as fast as a car on a highway. That's a pretty high acceleration. Typical cars typically aren't more than a couple of meters per second squared. 9.8 meters per second squared, as we discussed in kinematics, is the acceleration due to gravity, and it has its own symbol, lowercase g. And I just want to reiterate that if you have to worry about the y component of acceleration and it's only due to gravity, you can say that the y component of acceleration is minus g. But g itself is a strength, it's a magnitude, it's an absolute value. G itself is not negative. If you have to worry about acceleration and acceleration is down, you have to explicitly put the minus sign in front of g. G is not negative 9.8 meters per second squared. G is 9.8 meters per second squared. In the context of Newton's second law, if we're asking what is the force due to gravity, well, we know that force equals mass times acceleration. If gravity is the only force acting on an object, we would say that the gravitational force equals the mass times the gravitational acceleration. The magnitude of the gravitational force would be mg. And if I wanted to express it as a vector, I would say minus mg y hat. The minus because it's down, mg for the magnitude of the force, and the y hat to indicate parallel to the y-axis. A little side note, and this is sort of to set the stage for those of you who take Physics 150. We think of g as the acceleration due to gravity, but it's possible to show that an alternative set of units for little g is newtons per kilogram. And if we look at it in that context, g becomes more of a measure of the strength of the gravitational field itself. Newtons per kilogram, 9.8 newtons per kilogram. That means that for every kilogram of mass an object has, there's going to be 9.8 newtons of force. So 1 kilogram, the gravitational force is 9.8 newtons. 2 kilograms, the gravitational force is 19.6 newtons, and so on and so forth. So it's a measure of the strength. On the moon, the gravitational field strength is about 1.6 newtons per kilogram. On Mars, the gravitational strength is about 3.4 newtons per kilogram. So that's the gravitational force. You can always express the magnitude of the gravitational force as mg unless you have some extraordinary circumstances. The next force with which the force that you are encountering right now, because you are in contact with the surface, is the normal force. The normal force is a type of contact force. The normal force is what keeps you from falling through the chair you're sitting in, or from falling through the floor you're standing on. The chair or the floor is exerting an upwards force to counteract gravity. We call this the normal force because the direction of this force is always perpendicular to the surface against which the object is placed. If I have the object on the floor, then the direction of the normal force is straight up from the floor. If I have the object on a ramp, then the normal force on the object is perpendicular to the surface of the ramp. Maybe I'm pushing this object up against a wall. If so, the wall is exerting a normal force on the object perpendicular to the wall, so this would be an example where the normal force could be horizontal. It has to be, though, perpendicular to the surface against which the object is placed. The normal force is hard to calculate. There's no formula for the normal force. The normal force kind of magically balances out the other forces to allow for the motion that we see. A classic example of the normal force in action is you standing on a bathroom scale. Now, if it's just you standing on the bathroom scale, the gravitational force is pulling you down, and the scale is pushing up on you. And the reading on the scale is actually the normal force the scale requires to support you. If it's just you and the scale and gravity, then the normal force and the gravitational force must be equal to each other, and so the bathroom scale indirectly tells you the gravitational force, which we use the word weight for. But suppose you have a friend come along behind you, and they're not standing on the scale, but they place their hands on your shoulders and they push down on your shoulders. The reading on the scale goes up. The gravitational force acting on you has not changed. You still have the same weight. You have the same mass. You have the same weight. The gravitational force has not changed. But the reading on the scale goes up because now there's an additional attempt to push you down through the scale, and so the normal force responds to exactly as much as needed to keep you from falling through it. Similarly, if that same friend, still not standing on the scale, were to come up and partly support your weight, not lift you off completely, but partly support your weight, the reading on the bathroom scale goes down. Not because you lost weight, but because your friend supporting part of your weight means that the bathroom scale doesn't have to exert as much normal force. So the normal force goes down, the reading on the bathroom scale goes down. The normal force is a smart force, and from a practical consideration, that means you can't easily determine it. I should point out, as with the bathroom scale, there are cases where the normal force is not going to exactly counterbalance gravity, and it's even possible for the normal force to be in the same direction as gravity. The people at the top of the loop in this roller coaster, as we'll see in a later lecture, they are experiencing a downwards normal force in addition to the downwards force due to gravity. And if you're wondering why aren't these people falling out with all those downward forces acting on them, we'll get there, just not today. How do you handle the normal force? You still, despite the fact you don't have a formula for the normal force, you still need to include it in your free body diagrams. Make sure you know the surfaces with which the object is in contact. There could be more than one. If, for instance, you are leaning against a wall, there's a normal force between you and the wall that is horizontal. It's perpendicular to the surface of the wall. But then your feet are in contact with the floor. There's a normal force between the floor and your feet, and that force would be directed straight upwards. Make sure you know the angles of the surfaces, if it's a wall, if it's a floor, if it's a ramp, and make sure that those normal forces are drawn perpendicularly to the surface, pointing away from the surface. Now let's think about what I've been saying. Let's say you're on an elevator, and you're going to go up, you just push the button, the door is closed, and the elevator starts moving you up. Now, you are motionless, and then a little bit later you're moving up, so you must have accelerated upwards for at least a short period of time. During that upwards acceleration, what can we say about the normal force acting on you compared to the gravitational force acting on you? While you're accelerating upwards, does the elevator floor exert a normal force on you that's larger than the gravitational force, equal to the gravitational force, smaller than the gravitational force, or fluctuating around the gravitational force? There are times in which it's larger than the gravitational force, times during which it's smaller than the gravitational force while you're accelerating upwards. Think about it, and as always, if you have questions, let me know at the start of class. So there's no formula at all for a normal force, and we're going to find that there is a less than satisfying formula for the frictional force. But we still got to consider it. It is a factor in our day-to-day lives. So friction, that is also a force you encounter all the time, and sometimes friction really annoys us, but friction is essential to life. We couldn't move without friction, so we have to make sure that we understand it. It's just a part of our everyday lives. To understand friction, we first recognize that there are two different situations that involve friction. One is static, the other is dynamic, although dynamic is also called kinetic. So static friction, there's no motion across the surface. The object is not sliding across the surface. Now, you might think of it as a glass sitting on a table or something that's not moving. And yes, if I tilt the table slightly, the glass doesn't move. That means that we're in the realm of static friction. But it also turns out that if your car tires are operating correctly as you move across the road, that too is also in the realm of static friction. Dynamic friction is when the surfaces are sliding. So if I tilt the table on which my glass sits, and I tilt it enough that the glass starts to slide across the surface of the table. While the glass is sliding, we have surfaces in motion relative to each other. That's dynamic friction or kinetic friction. If you're driving your car across an icy patch and your tires start to spin and you start to skid across the road, you're actually in the realm of dynamic friction. The surface of the tire is not grabbing securely onto the road. It's sliding across the surface of the road, and so you get that skidding effect. Whether we have static friction or dynamic friction, we're going to take into account the fact that the frictional force is proportional to the normal force. So the larger the normal force, the larger the possible frictional force. But we are going to see that the static frictional force is a smart force. That makes it a pain in the rear. But the dynamic frictional force has a formula. Whether it's static friction or dynamic friction, though, we are going to take advantage of the fact that the frictional force is proportional to the normal force. If what I say isn't yet making sense, consider pushing two different objects across a horizontal floor. If one of them is a very light object, then the gravitational force acting on it is small, presumably the normal force acting on it is small, and it's easy to push. If it's a heavy object, then the gravitational force acting on it is large. It's likely the case that the normal force in return that is acting on it is large, and that means that pushing it across the floor is harder. So, if the normal force goes up, it's likely that the frictional force goes up as well. It's definitely true for the kinetic frictional case. The heavier the object, the greater the kinetic frictional force. The constant of proportionality between the frictional force and the normal force is called the coefficient of friction. The coefficient of friction is a unitless quantity. It's just a number. It's almost never bigger than 1. It is a positive quantity between 0 and 1. Frictionless would mean that the coefficient of friction is 0. The coefficient of friction comes in two varieties, one for the static case and one for the kinetic or dynamic case. The coefficient of friction is labeled with the lowercase Greek letter mu, which looks like a little bit like a very script-like letter U, but this is the lowercase Greek letter mu. And you see mu subscript S for the static situation, mu subscript K for the kinetic or dynamic situation. Every pair of surfaces has its own set of coefficients of friction. What do I mean by every pair? If I have wood on ice, if those are the two surfaces in contact with each other, there is a particular pair of mu-S and mu-K for those two surfaces. If the wood is in contact with concrete, there's a different set of mu-S and mu-K. If steel is in contact with ice, there's yet another set of mu-S and mu-K. Or if it's wood in contact with steel, a wooden surface in contact with a steel surface, yet another set of mu-S and mu-K. There is no formula to calculate mu-S or mu-K. These are strictly associated with the pair of surfaces in contact with each other. I either have to give these values to you, or it becomes the goal of the problem to solve for it. There's no theoretical value. Just know that any of these greater than 1 is under exceptionally rare circumstances. They are almost exclusively between the 0 and 1, and they are unitless quantities. Mu k is less than mu s. For any given pair of surfaces with a mu s and a mu k is less than mu s. You have encountered this phenomenon before, I'm sure. It is often hard to get an object moving, but once you get it moving, you don't need to push it quite as hard. Well, that's because mu s is greater than mu k. When the object is not yet moving, you're in the realm of static friction. The static frictional force can be higher than the kinetic frictional force. So you have to first get it moving. You have to overcome that maximum static frictional force. But once you get it moving, you don't need to push quite as hard because the kinetic frictional force is a little bit less. We can calculate the kinetic frictional force. The kinetic frictional force is equal to the coefficient of kinetic friction times the normal force. The static frictional force is a bit more challenging because it is a smart force. We will look at examples, so if this next statement slips past you, I'm not too concerned. I will cover this. But the maximum possible static frictional force is equal to the coefficient of static friction times the normal force. We'll discuss that over time. When you have a situation with a frictional force, what are the general steps you should follow? First, determine if it's the static frictional force or the kinetic frictional force. Determine the direction of the frictional force. If an object is moving across a surface, then you know that the kinetic frictional force opposes the direction of motion. I don't care if the object is speeding up, slowing down, or moving at constant velocity, the kinetic frictional force always opposes the direction of the motion. But if the two surfaces are not sliding with respect to each other, it's more vague. If there is an attempt to push an object, then the static frictional force would be in a direction opposite to it. But we'll see situations where the static frictional force defies what our intuition might be telling us. Determine the normal force. Remember that the normal force is instrumental in determining the frictional force. So if you have the information to figure out the normal force, do it like we did in the earlier example. If it's kinetic friction and you know the coefficient of kinetic friction, then you find the kinetic frictional force by doing mu k times the normal force. If it's static friction, it's not so straightforward. It's complicated. Here's an example throwing you a bunch of information at once. In this example, we don't know the coefficient of friction between a mass and a floor. The mass is 21.2 kilograms, and at least it's on a horizontal floor. We are pushing on the mass to the right with a 51.2 Newton force. The mass is accelerating at a rate of 0.912 meters per second squared to the right. What is the coefficient of kinetic friction? That's the only one that we can determine. If the object surface is in motion relative to the floor, this is kinetic friction. This is dynamic friction. We aren't going to learn jack about static friction in this problem because the object is already in motion across the surface. Our starting information, the mass is 21.2 kilograms. We have the x component of the acceleration is 0.912 meters per second squared. The object is not moving in the vertical direction, so the y component of the acceleration is 0. And we are told that the pushing force is 51.2 newtons. We've drawn our three-body diagram. We have the pushing force to the right, and it's parallel to our x-axis, so it's at 0 degrees. The frictional force opposes the direction of motion, so it's to the left. It's at an angle of 180 degrees. The normal force points directly up, 90 degrees. The gravitational force points directly down at 270 degrees. Because the normal force is strictly along the y-axis, we need to start with the y stuff, the y information to figure that out. Basically, if everything is purely vertical, we can cut to the chase a little bit and say that the net force is equal to forces up minus forces down. Now, I could do normal force is the sine of 90 plus the gravitational force times the sine of 270. And if I do that, I get the normal force minus the gravitational force. I could also include the pushing force times the sine of 0, but the sine of 0 is 0. No contribution there. I can do the frictional force times the sine of 180, but the sine of 180 is 0, so no contribution there. The long and short of it is our second law applied to the y-axis. We get the normal force minus the gravitational force equals 0. So therefore, the normal force must be equal to the gravitational force. The gravitational force is equal to mg. M is 21.2, g is 9.8, because this is presumably near the surface of the Earth. So we can calculate the normal force. Now we jump to the x-axis stuff. And again, because things are either perfectly vertical or perfectly horizontal, we can cut to the chase. And for x-axis stuff, in these circumstances, we can say stuff pointing to the right minus stuff pointing to the left. The pushing force is to the right, the frictional force is to the left, so I can say the pushing force minus the frictional force. And that's going to be equal to m times the x component of the acceleration. I don't know the frictional force, but I do know the pushing force is 51.2. I know the mass, and I know the x component of acceleration. So I can solve for the magnitude of the frictional force. I get that the frictional force, after a little bit of recombining, I get that the frictional force is basically 31.9 newtons. By the way, all of these F's that you see right here, I should come up with a positive value because each of these F's represents a positive quantity. They represent a magnitude. So the frictional force has a magnitude of 31.9 newtons, and we know that the frictional force is equal to mu times the normal force. In this case, mu k, because the surfaces are sliding. The normal force is equal to mg. So 31.9 must be equal to mu k times 21.2 times 9.8. 9.81 is slightly more precise. And you go through the numbers, and you get that mu k is equal to 0.153. Perfectly reasonable value for a coefficient of friction. Quick follow-up question to the idea of friction. Which of the following is true? You're pushing a wooden crate across the floor. You decide to turn the crate onto one end because you think because you see that one end has a smaller surface area. If that end has a smaller surface area and you push on the crate with the same force, or if you want to push on the crate to achieve the same speed, I should say, what force should you apply? Should your new force be 4 times as great as the old force, twice as great, equally great, half as great, 1/4 as great as the original force? Think about it, but don't think too hard. Don't overthink it. Tension. Tension occurs when there's a rope, a string, a cord, a cable, something like that is connecting two objects. The trick about tension, well, 2 tricks. The first trick is the tension force on object A is going to have the same magnitude as the tension force on object B, assuming object A and B are connected by the same rope. The second trick is that the direction of the tension force is in the direction of the rope where it attaches to the object. So you see a picture here of a horse and a calf being roped together. If I were to draw a free body diagram of the horse on the lower left and a free body diagram of the calf on the lower right, because of the rope connecting them, there is a tension force on the horse, there is a tension force on the calf, but I have drawn the tension force, and you can see the purple text representing the tension. Those arrows have the same length, but they are in exactly the opposite direction. On the horse, the tension force points along the rope to the calf. On the calf, the tension force points along the rope to the horse. So wherever there's a rope, cord, cable, string, whatever, there's a tension force. The tension force is directed along that string, rope, cable, cord, whatever. Whew, that's enough.